In this video, we're going to revisit our idea of heat transfer, but we're going to see it in a new light that's going to lead to a new kind of mathematical problem. What we're going to consider is a simple cooling fin, like the one here, very long in proportion to its cross-section. And the question we'd like to ask, given that there's going to be some heat coming in from the bottom and radiating out from the fin, the question we'd like to ask and answer is how quickly is the heat radiating out? It's a reasonable design question because that'll inform how large a fin, how long a fin, what material the fin is made out of. And specifically, we would like to itemize that list. What factors would affect the rate of heat transfer? Definitely material, the cross-sectional area, and also other derived properties from that. This area is also going to affect the exposed surface area. So that's going to be another element. And the other things that might affect it would be potentially the temperatures. If we look at the literature for cooling and heating and cooling problems, what we call T infinity is the temperature of the environment. And the rationale there is that the temperature at infinity or a long way away is some value that's constant and not affected by the heat loss that we see here. We'll also need the temperature at the base to see what the temperature differences are that drive the heat transfer. So those temperatures are also going to be important. And of course, we could also add the other physical dimension here, the length of the fin. And that captures a lot of the ingredients that we'll want. If there's anything else that we need, we'll see if it turns up. The challenge then is going to be to figure out how those properties tie back to our big question of how much heat is radiating out of this fin. Well, the main challenge that we're facing is that temperature differences are what drive temperature change or heat flow. Fair enough. The problem or the challenge here in this kind of fin design is that the fin is going to be hottest at the base, but then as we move up the fin itself, heat will have radiated away, and you're eventually going to have a cooler end at this end of the fin. And so that's going to play a role in how we compute the heat loss because the temperature difference varies with the position along the axis here or along the fin. Let's define that somehow. Let's call that x, with x equals 0 at the base, so that temperature difference varies with what x is. Okay, we can work with that. The way we can get around that restriction is by starting to look at a small piece of this puzzle. And imagine we're taking a small slice, a small cutout of this shape, and that cutout will be, in very traditional calculus terms, delta x thick. Then we can look at how much heat loss there would be out of that one portion of this entire fin. Well, let's look at the ingredients. We're going to have the heat flow out of that slice is going to be proportional to the temperature difference. We'll need to include that. And it's also going to be proportional to the surface area. If we doubled this surface area by making it a larger fin, we would double the amount of heat loss, or double the rate of heat loss. And that actually captures most of what we want. The materials would affect the constant of proportionality, but we'll get that when we make a formula. But these are the only design elements that are going to play a role. So let's talk about the temperature difference. If we talk about the temperature on this element, and noting that the temperature changes as we go from the base to the tip, we would define maybe the temperature on that element there, on that ingredient slice, as T of x. And we would contrast that with the temperature in the environment, T infinity. So the temperature difference we're talking about is the difference between the temperature on this slice and the temperature of the environment, T infinity. The other element was a surface area, and that we can get by unrolling this size here, this slice here, and if we unroll it, we'll get some value for the perimeter. In fact, let's actually use the perimeter. And if we take that perimeter and multiply it by the other dimension we have, which is delta x, that will give us the area that's exposed to the environment. And let's give that a name. We'll just call it P, and then delta x for the surface area. With those ingredients and the idea that the temperature difference and the surface area are the main ingredients to heat flow, the heat flow out of the slice is going to be equal to, well, it's proportional to, which is the same as equals to a constant times T of x minus T infinity times P times delta x. So temperature difference and something to do with the area is going to affect all this. That only captures the heat flow out of one little segment. Hey, if we want to find the total heat flow, what do? We use an integral. Total heat flow will be an integral of exactly these properties here. So K, temperature on the fin minus the environmental temperature times P, but instead of delta x, that becomes a dx, and we'll integrate from x equals 0 all the way out to the end. Let's give that a name. Let's call the length of this fin L. So an integral from the base to the tip, adding up the effect of the temperature difference and the perimeter along the way. So that is lovely. Conceptually, we know what we need to do. There's going to be a little bit of focus here because T of x is actually the only variable in here that complicates this. Everything else, K, T infinity, and P, are all constants. So we're going to need to take a closer look at that T of x. Just for a moment here, recapitulating that idea, the sum of the delta x's, repeating what we get here. We had the integral from x equals 0 to x equals L of a constant times T of x minus that constant T infinity times the perimeter times dx. Now, if we want to make this a little bit easier to work with, and we will when we get into the MATLAB, let's make that T infinity 0. It doesn't have a huge effect. We could integrate it separately, so this is not a major concession, but it'll certainly make our integral look a lot nicer. It just becomes K times P times our temperature times dx. And we'll make one more note while we're here, which is that this K is in fact usually called an H, because an H is what we call convection coefficients. And those are the variables or the values that dictate how quickly heat flows between two materials. And that's what we're talking about here. If we're talking about the heat loss out of this slice, it's jumping from the material of the fin to the material of the environment. But that's it. We're good to go. So what's next? Well, we would need to find out a formula for this T of x. Well, fortunately, there is a nice differential equation that describes how to do this. And if you think back to whatever your math course was that did differential equations, 225, 232, some other variation on those numbers, you would learn how to solve this. And the idea here is if we're trying to predict the temperature as a function of x along the fin, where x is the distance along that fin, we know what it's going to look like roughly. It's going to be cooling down. But what does that actual graph look like? Well, I don't know. Well, there's some nice physics rules that come into play. And this is a second order dE. And if you did all the stuff that you learned in your differential equation class, you could solve that. It's actually fairly simple. There's just some nasty constants, but nothing really super challenging. It's all linear. However, even if you do that correctly, here's what you get as your solution. So at the end of the day, you would want T of x equals. That's what the solution to this differential equation is. If you went through all the processes and did the calculations and, this is what you get. This is nothing that anybody really likes to look at. It's not a pretty formula, but it describes mathematically as a formula for the shape of a curve like this, where we have a temperature at the end and it goes on. But nobody likes this. We can see some of the ingredients. We've got H in there. The K actually is a new K, That is the conduction coefficient. So it's how quickly stuff flows or heat flows through the material itself. The perimeter's in there. This m value is some nasty like square root of mk over h or something. So even the constants in here are ugly and complicated. So this is our T. You could find it. It would take a chunk of work. Take about a page probably to get from here to here using the techniques from your differential equation class. However, that's not even the hard part. I mean, this is challenging. But then we also have the next step, which is we want to be able to integrate that. So our next step is to take this. Our goal here is to compute. Let's paste that again. We don't want that part now. We just want to integrate the coefficient of convection times P times that dx. So look at all the x's in here and imagine trying to integrate that from 0 to the length of our fin. All right. That is going to be even nastier. I will not sugarcoat that. However, conceptually, it's straightforward. We want to find the area under that curve. And if you actually look at the curve that we get, here we made a base temperature of 100 degrees and external environmental temperature of 0, like we said earlier. What you get is a nice curve, and in principle, we just want to find the area underneath that curve. So now we're just faced with the quandary of how would we evaluate that integral in a way that seems practical and gets us to the answer as efficiently and as cleanly as possible. That's where we're going to continue in the following videos.